Welcome! In this session, we will explore LeetCode problem number 1634, add two polynomials represented as linked lists. This problem challenges us to carefully manipulate linked lists to represent and merge polynomials efficiently. Let's dive in to dissect the problem and walk through the solution. In this problem, we are working with polynomials represented as linked lists. Each node in the linked list contains two key pieces of information: the coefficient of a term and the power of that term. These terms are ordered in descending order by their power, meaning the highest powered term appears first. Our task is to add two such polynomials together, combining like terms where the powers match, and return the resulting polynomial as a new linked list. This result must also maintain the descending order of powers. If two terms with the same power sum to 0, we exclude the term from the result. The input consists of two linked lists, poly1 and poly2, each representing a polynomial. Let's now look at how the output is structured. The output of this problem is another linked list, where each node represents a term in the resulting polynomial. Each node contains the coefficient and power of a term, and the terms are arranged in descending order by power. If adding the two polynomials causes all terms to cancel out, the output will simply be an empty linked list. To better understand this, let's consider an example. Suppose the first polynomial is represented as 1, 3, 2, 2, 3, 0, which stands for 1x cubed plus 2x squared plus 3. The second polynomial is 2, 1, 3, 0, or 2x plus 3. When we add these two polynomials, the result is 1x cubed plus 2x squared plus 2x plus 6, which is represented as the linked list 1, 3, 2, 2, 2, 1, 6, 0. This example shows how like terms are combined, and the result remains sorted by descending power. Let's look at another example to reinforce the concept. Here, poly1 is 1, 4, 3, 3, 4, 0, representing the polynomial 1x to the power of 4 plus 3x cubed plus 4. Poly2 is 1, 3, 4, 0, representing 1x cubed 4. When we add these, the terms with power 4 remain as 1x to the power of 4, and for power 3, we combine 3x cubed and 1x cubed to get 4x cubed. The constant terms, 4 and minus 4, cancel each other out, so there's no constant term in the result. The resulting polynomial is 1x to the power of 4 plus 4x cubed, and this is represented as the linked list 1, 4, 4, 3. Notice how terms with the same power are combined, and terms that cancel out are excluded from the result. In this third example, poly1 is an empty polynomial, while poly2 is 5, 1, 2, 0, representing 5x plus 2. Since the first polynomial is empty, there are no terms to combine with poly2. Therefore, the result is simply the second polynomial as it is, and it is represented as the linked list 5, 1, 2, 0. This highlights that when one of the input polynomials is empty, we simply return the other polynomial unchanged as the result. Now, let's move on to the constraints of the problem. There are a few important constraints to keep in mind for this problem. First, the number of nodes in each input linked list can range from 0 to 10,000. Second, the coefficient of each term is an integer, which can range from minus 10,000 to 10,000, while the power of each term is always a non-negative integer between 0 and 10,000. Both input linked lists are guaranteed to be sorted in descending order by power, and the resulting linked list must also adhere to this order. Additionally, if two terms with the same power add up to 0, that term must be skipped in the result. Finally, if both input linked lists are empty, the output should be an empty linked list. These constraints ensure clarity and consistency in how the problem is approached and solved. To solve the problem of adding two polynomials represented as linked lists, we need to merge these lists efficiently while ensuring the result is in the correct order. Each node in the linked list contains two pieces of information: the coefficient and the power of the term. Our goal is to combine terms with the same power and produce a new linked list where terms are sorted in descending order of powers. One possible approach to achieve this is the brute force method. Here, we treat the two linked lists as if merging two unsorted lists. For each term in the first list, we iterate through the second list to find terms with matching powers. When we find a match, we combine their coefficients. If no match is found, the term is appended to the result list. However, since this process can create an unordered result, we also need to sort the final list by descending powers. While straightforward, this approach requires nested iterations and a sorting step, making it inefficient for larger inputs. The time complexity is O, m asterisk n plus k asterisk log, k, where m and n are the lengths of the two input lists, and k is the total number of terms in the result. It also requires O, k, space for the result list. The brute force method has significant drawbacks, particularly its inefficiency due to the nested iterations and the additional step of sorting. To address these issues, we can use a more efficient technique, the two-pointer merge approach. This method takes advantage of the fact that the input linked lists are already sorted by descending powers. By using 2 pointers, one for each list, we can merge the lists in a single pass without any unnecessary comparisons or sorting. The process involves comparing the powers of the terms at the 2 pointers. If the power of the term in the first list is greater, we append that term to the result and move the pointer in the first list forward. If the power of the term in the second list is greater, we append that term instead and move the pointer in the second list. If the powers are equal, we combine the coefficients, append the resulting term, and move both pointers forward. Once we've processed both lists, any remaining terms are appended to the result. This approach is highly efficient with a time complexity of O, m plus n, where m and n are the lengths of the two input lists, and it requires only O(1) additional space, as the merge is performed in place. Another alternative is a hash map-based approach, which offers a different way to combine terms with the same power. In this method, we use a hash map to store terms, where the keys represent powers and the values represent the corresponding coefficients. First, we traverse the first linked list and add each term to the hash map. Next, we traverse the second list and update the coefficients in the hash map for any matching powers. Once both lists are processed, the hash map contains all the terms, grouped by their powers. To construct the result linked list, we traverse the keys of the hash map in descending order, creating nodes for each term based on the combined coefficients. While this approach simplifies the process of combining terms and avoids nested iterations, it has a higher space complexity due to the use of the hash map. The time complexity is O, m plus n plus k asterisk log, k, where m and n are the lengths of the input lists, and k is the number of unique powers. The space complexity is O, k, which can be significant if the number of unique powers is large. Among the three approaches, the two-pointer merge strategy stands out as the most efficient and elegant solution. By leveraging the sorted nature of the input lists, it minimizes redundant computations and avoids the overhead of sorting or auxiliary data structures. Unlike the brute force method, it eliminates the inefficiencies of nested iterations, and unlike the hash map approach, it achieves optimal space efficiency by performing the merge in place. With a time complexity of O, m plus n, and constant additional space, this approach is ideally suited for the problem's constraints. The trade-offs between the methods are clear. While the brute force approach is conceptually simple, it is computationally expensive for large inputs. The hash map method improves time complexity but at the cost of higher space usage. The two-pointer approach strikes the perfect balance, making it the optimal choice. The key insight here is recognizing that the input lists are already sorted by descending powers. This allows us to use the two-pointer technique, which simplifies the process and avoids unnecessary computations. This realization is that aha moment that leads to the most effective solution. To solve the problem of adding two polynomials represented as linked lists, we need to focus on the structure and order of these lists. Each node in the linked list represents a term in the polynomial, with a coefficient and a power, and the terms are sorted in descending order based on their powers. Our goal is to create a new linked list that represents the sum of these polynomials, while ensuring that the terms remain in descending order and that we combine terms with the same powers. The algorithm begins with initialization. We create a dummy node to serve as the starting point of our resulting linked list. This dummy node simplifies managing edge cases, such as empty input lists. We also use a pointer, called tail, to help build the result list as we process the terms. Finally, we set up two pointers, P1 and P2, to traverse through the input linked lists, starting at their respective heads. This setup lays the groundwork for efficiently merging the two lists. Now, we traverse through both linked lists simultaneously. While neither list is exhausted, we compare the powers of the current terms. If the power in the first list is greater, we append the term from the first list to the result and move the pointer for the first list forward. If the power in the second list is greater, we append the term from the second list instead and move its pointer. When the powers are equal, we combine the coefficients of the two terms. If the resulting coefficient is non-zero, we append a new node with this combined coefficient and the common power. In this case, both pointers move forward. Once one of the lists is fully traversed, we append any remaining terms from the other list to the result. This ensures that all terms from both polynomials are included in the final result, maintaining the descending order of powers. The final step of the algorithm is to return the resulting linked list. Specifically, we return the node following the dummy node, as this represents the head of our new polynomial. There are several key insights to highlight about this approach. First, since the input lists are already sorted by descending powers, we can merge them efficiently in a single pass, similar to the merge step in merge sort. Second, we handle terms with zero coefficients by simply skipping them. This ensures the result list contains only meaningful terms. Finally, the algorithm is efficient, running in linear time relative to the combined length of the two input lists. Each node is processed exactly once, making it highly scalable. The use of linked lists and a dummy node provides the flexibility and simplicity needed to handle edge cases effectively. It's important to consider several edge cases when implementing this algorithm. If one of the input lists is empty, we simply return the other list as the result since there's nothing to add. If both lists are empty, we return null, as there's no polynomial to represent. Another edge case occurs when all terms with the same power cancel out due to their coefficients summing to zero. In this scenario, we ensure these terms are excluded from the result to avoid unnecessary nodes. Additionally, the algorithm must handle cases where one polynomial has terms with much higher or much lower powers than the other. By iterating through the list sequentially, we can seamlessly manage these differences and produce a correct result. Let's walk through an example to see how the algorithm works step by step. Suppose we have two input polynomials. The first is 4x superscript 3 plus 3x superscript 2, and the second is 5x superscript 3 plus x. We start by comparing the leading terms, 4x superscript 3 and 5x superscript 3. Since the powers are equal, we combine their coefficients, resulting in 9x superscript 3, which we append to the result. Next, we move both pointers forward and compare 3x superscript 2 with x. Here, 3x superscript 2 has a higher power, so we append it to the result and advance the pointer for the first list. At this point, only the term x remains in the second list. We append it to the result, completing the process. The final output is 9x superscript 3 plus 3x superscript 2 plus x, which represents the sum of the two input polynomials. Finally, let's consider some optimizations to improve both the clarity and efficiency of the algorithm. By directly combining coefficients when powers match, we avoid unnecessary node creation, making the result list cleaner and more efficient. The use of a dummy node simplifies edge case handling, reducing the need for additional checks or conditional logic. Additionally, by skipping terms with zero coefficients, we ensure that the resulting polynomial is minimal and contains only meaningful terms. These optimizations not only streamline the implementation but also ensure the algorithm remains efficient and robust, even for edge cases and large inputs. Here, we start by defining a class list node to represent the nodes of our linked list, where each node stores a term of the polynomial. Each term has a coefficient, a power, and a next pointer to connect to the next term. Then, we define the addPoly method in the solution class, which will handle the addition of two polynomials represented as linked lists. We initialize a dummy node, dummy, to serve as the starting point for our result linked list, and a pointer current to help us build the result list. Next, we enter a loop to traverse through both input polynomials, poly1 and poly2. Inside the loop, we compare the powers of the current terms. If the power of the term in poly1 is greater, we add the term to the result linked list. If the power of the term in poly2 is greater, we add the term instead. If the powers are equal, we combine the coefficients of the two terms. If the sum of the coefficients is non-zero, we add the resulting term to the result list. Finally, if a node is added, we move the current pointer forward to continue building the result. After processing terms with matching powers, there may still be remaining terms in either poly 1 or poly 2 that need to be added to the result. To handle this, we use two separate while loops. The first loop processes any remaining terms in poly 1, adding each of them as a node to the result list. Similarly, the second loop processes any remaining terms in poly 2. Within each loop, we create a new node for the current term, link it to the result list, and advance both the current pointer and the respective polynomial pointer. Once all terms from both polynomials have been added, the dummy node's next pointer points to the head of the result linked list. We return this pointer as the final answer, giving us the sum of the two polynomials represented as a linked list. Here, we start by defining the list node class, which represents a single term in our polynomial linked list. Each node contains three components: the coefficient of the term, the power of the variable, and a reference to the next node. The constructor initializes these values and sets the next pointer to null. Then, in the solution class, we define the method addPoly, which will take two polynomial linked lists, poly 1 and poly 2, as input and return a new linked list representing their sum. To begin, we create a dummy node to serve as the head of the result linked list, and a current pointer that will help us build the list as we iterate. Inside the while loop, we compare the powers of the current terms in poly 1 and poly 2. If the power in poly 1 is greater, we add the term to the result list and move poly 1 forward. If the power in poly 2 is greater, we do the same for poly 2. However, if the powers are equal, we add their coefficients together. If this sum is non-zero, we create a new node with the combined coefficient and shared power, ensuring that only meaningful terms are added to our result. If a node was added to the result list during any iteration, we update the current pointer to point to the newly added node. Once one of the input lists is fully traversed, we handle any remaining terms from the other list. This is done using two separate while loops. If poly 1 still has terms, we append them directly to the result list, advancing the current pointer in poly 1 as we go. Similarly, if poly 2 has terms left, we append those as well, following the same process. This ensures that all terms from both input polynomials are included in the result. Finally, we return dummy.next, which points to the head of the result linked list, effectively skipping over the dummy node. This implementation guarantees that we handle all cases, including mismatched powers and zero coefficients, while maintaining the correct order of terms in the resulting polynomial. In this example, we are adding two polynomials that have overlapping powers. We begin by initializing a dummy node with coefficient 0 and power 0, and we set a pointer, current, to this dummy node. Next, we compare the terms from poly 1 and poly 2. The first terms are 3x to the power of 4 from poly 1 and 5x to the power of 4 from poly 2. Since their powers are equal, we add the coefficients, 3 plus 5 equals 8. We then create a new node with coefficient 8 and power 4, attaching it to current.next. After this, we advance both poly 1 and poly 2 to their respective next terms, which are 2x cubed and 2x to the power of 1, and move the current pointer to the newly created node. Next, we compare the current terms of poly 1 and poly 2. The term 2x cubed from poly 1 has a higher power than 2x to the power of 1 from poly 2. Since poly 1 has the larger power, we create a new node with coefficient 2 and power 3, attaching it to current.next. We then advance poly 1 to its next term, 1x to the power of 0, and move current to the new node. Now, we compare 1x to the power of 0 from poly 1 with 2x to the power of 1 from poly 2. This time, poly 2 has the larger power, so we create a new node with coefficient 2 and power 1, attaching it to current.next. We advance poly 2 to its next term, 3x to the power of 0, and move current to the new node. Finally, we compare 1x to the power of 0 from poly 1 with 3x to the power of 0 from poly 2. Since their powers are equal, we add the coefficients, 1 plus 3 equals 4. We create a new node with coefficient 4 and power 0, attach it to current.next, and advance both poly 1 and poly 2 to none. The current pointer moves to the last added node. After completing the comparisons, the merged polynomial is 8x to the power of 4-2x cubed 2x to the power of 1-4x to the power of 0. Now, let's look at another example where the two polynomials do not have any overlapping powers. Here, poly 1 is 4x cubed 3x to the power of 1, and poly 2 is 5x squared 2x to the power of 0. We start by initializing a dummy node and setting current to it. The first terms are 4x cubed from poly 1 and 5x squared from poly 2. Since 4x cubed has a higher power, we create a new node with coefficient 4 and power 3, attaching it to current.next. We then advance poly 1 to its next term, 3x to the power of 1, and move current to the new node. Now, we compare the current terms, 3x to the power of 1 from poly 1 and 5x squared from poly 2. Since 5x squared has a higher power, we create a new node with coefficient 5 and power 2, attaching it to current.next. We then advance poly 2 to its next term, 2x to the power of 0, and move current to the new node. Next, we compare 3x to the power of 1 from poly 1 with 2x to the power of 0 from poly 2. Here, 3x to the power of 1 has the higher power, so we create a new node with coefficient 3 and power 1, attaching it to current.next. We advance poly 1 to none and move current to the newly added node. At this point, poly 1 is none, but poly 2 still has a remaining term, 2x to the power of 0. We add this term by creating a new node with coefficient 2 and power 0, attaching it to current.next. We then advance poly 2 to none. As a result, the merged polynomial is 4x cubed 5x squared 3x to the power of 1 2x to the power of 0. Let's explore a third example where some terms cancel out because their coefficients sum to 0. Here, poly 1 is 3x cubed minus 3x squared, and poly 2 is 3x squared 2x to the power of 0. We initialize a dummy node and set current to it. The first terms are 3x cubed from poly 1 and 3x squared from poly 2. Since 3x cubed has the larger power, we create a new node with coefficient 3 and power 3, attaching it to current.next. We then advance poly 1 to its next term, minus 3x squared, and move current to the new node. Next, we compare minus 3x squared from poly 1 and 3x squared from poly 2. Their powers are equal, so we add the coefficients, minus 3 plus 3 equals 0. Since the result is 0, we skip adding a node and simply advance both poly 1 and poly 2 to their next terms. At this point, poly 1 becomes none, but poly 2 still has one remaining term, 2x to the power of 0. We add this term by creating a new node with coefficient 2 and power 0, attaching it to current.next. We then advance poly 2 to none. The final merged polynomial is 3x cubed 2x to the power of 0. The time complexity of the add poly function is determined by how the algorithm processes the terms in the two input polynomials. Since we are iterating through both input linked lists, the time complexity is O, m plus n, where m is the number of terms in the first polynomial, and n is the number of terms in the second. First, the main while loop compares the powers of the terms in poly 1 and poly 2. For every iteration, one term from either poly 1 or poly 2 is processed and added to the result linked list. This continues until one of the lists is exhausted, which takes O, min, m, n steps. After that, the remaining terms from the non-empty list are appended to the result using additional while loops. These loops process the remaining terms in O, max, m, n time. When we combine these two steps, every term in both polynomials is processed exactly once, giving us the overall time complexity of O, m plus n. The space complexity of the add poly function is primarily determined by the size of the result linked list. For each term in the input polynomials, a new node is created in the output. In the worst case, all terms from both poly 1 and poly 2 are included in the result, which means O, m plus n, space is required for the result linked list. Beyond this, there are no additional data structures being used. The algorithm only relies on a few temporary variables, such as pointers like current or dummy, which consume constant space, O1. Therefore, the total space complexity is dominated by the result linked list, and it is O, m plus n. This efficient use of space ensures that the algorithm is well suited for adding large polynomials represented as linked lists. The performance of the algorithm can also be analyzed across different cases. In the best case, if one polynomial is empty, the algorithm simply processes the other polynomial. Here, the time complexity becomes O, m, or O, n, depending on the size of the non-empty polynomial. In the average case, we assume that the two polynomials have comparable lengths and that their terms have non-overlapping powers. The time complexity remains O, m plus n, as each term is processed exactly once. In the worst case, both polynomials have terms with overlapping powers, requiring every term to be compared and added to the result. Even in this case, the time complexity is still O, m plus n. To contrast, a brute force approach would iterate through the first polynomial for every term in the second, resulting in a much higher time complexity of O, m asterisk n. The optimized approach achieves O, m plus n, by leveraging the sorted order of the input lists, making it significantly faster. In terms of space, both approaches require O, m plus n, for the result linked list, but the brute force method may use extra temporary storage, making it less space efficient overall. To formally validate the time complexity, we can observe that the total number of iterations across all loops is limited by the combined lengths of poly 1 and poly 2. Each term is processed exactly once, whether in the main loop or during the appending of remaining terms. This ensures that the overall time complexity is O, m plus n. Similarly, the space complexity is determined by the size of the result linked list, which contains at most m plus n nodes. This leads to a space complexity of O, m plus n. In conclusion, the optimized approach is both time and space efficient. By processing each term linearly and avoiding unnecessary computations, the algorithm achieves a complexity that is directly proportional to the size of the input polynomials. When working with this problem, there are some common mistakes you should watch out for. First, forgetting to handle cases where one or both input linked lists are empty can lead to runtime errors. You should always check if either list is null or if it reaches the end early. Next, be careful when assuming the input linked lists are sorted by power. If you don't verify this, or if the powers are not in descending order, the result will be incorrect. It's a good practice to confirm the order or pre-process the lists to ensure they are sorted. Another frequent issue is comparing powers incorrectly. For example, if you use a less than comparison, power underscore 1 power underscore 2, instead of comparing for descending order, it can disrupt your merging logic. Additionally, you should handle zero coefficients properly. Adding terms with zero coefficients to the result list creates unnecessary complexity, so these should be skipped after addition. Finally, modifying the input lists unintentionally is a common pitfall. If you alter the structure of the original lists during operations, it can lead to unexpected behavior, especially if the lists are needed later. To avoid this, consider using dummy nodes or creating new nodes for the result list instead of directly modifying the inputs. To maximize your performance in interviews, it's important to recognize key insights about this problem. First, this is a variation of the classic merge two sorted lists pattern. If you master that pattern, it will help you solve many similar linked list problems more effectively. In terms of complexity, the goal is to achieve O, n plus m, where n and m are the lengths of the input linked lists. Avoid solutions with nested loops, such as O, n asterisk m, as they are inefficient. Also, be prepared to discuss edge cases, such as when one list is empty, when there are overlapping powers in the terms, or when all terms have zero coefficients. These scenarios often come up during interviews. Additionally, interviewers might ask follow-up questions, such as how you would handle polynomials represented in alternative formats, like arrays or hash maps. Be ready to explain how your approach would adapt to these variations, as this demonstrates a deeper understanding of the problem. This problem is closely related to several other linked list problems that can help reinforce the core concepts. For example, LeetCode 21, Merge Two Sorted Lists, uses similar merging logic and is an excellent problem to practice the foundational pattern. Another related problem is LeetCode 2, Add Two Numbers, which involves adding numbers represented as linked lists, but in this case, it's done digit by digit. Similarly, LeetCode 445, Add Two Numbers 2, is another version of this problem where the numbers are represented in reverse order. Lastly, LeetCode 708, Insert into a Sorted Circular Linked List, involves working with sorted linked lists and is useful for understanding how to insert and merge nodes efficiently. Practicing these problems will strengthen your ability to handle a wide range of linked list scenarios. There are also alternative approaches to solving this problem, each with its own trade-offs. One option is to use a dictionary, or hash map, where the powers of the terms are stored as keys and their coefficients as values. This approach eliminates the need to traverse the linked lists during the merge process, but it requires additional space proportional to the number of distinct powers, O, k. This can be particularly useful if the input lists are unsorted. Another approach is array-based. You can convert the linked lists into arrays, merge them, and then convert the result back into a linked list. While this simplifies the merging logic, it introduces overhead due to the conversions and requires additional space. Lastly, you could modify the input linked lists directly in place to save memory. While this is space efficient, it risks corrupting the original data structure, which may not be allowed in an interview setting. Understanding these trade-offs will help you choose the best solution for different scenarios. Great job! We reviewed how to tackle problem number 1634 by merging linked lists representing polynomials. Key takeaways include understanding linked list manipulation and edge case handling. Thanks for joining, and don't forget to like, subscribe, and keep honing your skills. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!